So, good day. For this session, we will be discussing cybersecurity intrusion prediction. For section 1, we have code, model, and dataset. For the dataset, it was published on Kaggle. It is a structured tabular dataset representing simulated and real network session records, each label with whether an intrusion was detected or not. It is designed specifically for binary classification with machine learning models. So the dataset type is a structured network session log with tabular CSV file. Then the task will be binary classification. Intrusion means zero or normal. One means attack. Features, it has 15 columns. Then for the target label, we have intrusion detection, which is 0 or 1. These are the key features column in the dataset. Feature 1, network packet size. The type is numeric. Feature 2 is protocol type, which is a categorical. It is encoded for machine learning model. Login attempts numeric, session duration numeric, bytes sent and bytes received numeric, IP reputation score numeric, failed logins numeric, encryption use categorical, so it encoded as binary flag 1 or 0. Then browser type categorical, it encoded to detect unusual agents, feature unusual time access binary, and the intrusion detected, which is the dependent variable, one intrusion detected, zero normal traffic. The full code pipeline is this one. So step one, we need to load the data. Step two, we need to do a exploratory data analysis or EDA. Step 3, we need to pre-process the data. Step 4, we need to train and test split or splitting to train and test. Step 5, we need to train models. And step 6, we need to evaluate it. So let's proceed with the Kaggle notebook. First, make sure that we are using GPU for the accelerator. Then we need to import the libraries. So let's import it right now. We use pandas, numpy, matplotlib, seaborn, and sklearn, such as model selection, ensemble tree learning, linear model, naive bias, and metrics and pre-processing. Then let's see if the data was loaded. Yes, it is. Data info. We have the column. We have 9,537 entries, and we have missing data. And for this, we need to drop, wait for a while, encryption use because um, it has more null values or missing values. As you can see here, it's almost 2,000 or 1,500 rows. So we need to drop it, then describe, check if there are null values. Okay, we're good. If there are duplicate, EDA. So total attack 0, 1 is almost 4,000. We need to encode the protocol type and browser type, because uh, according to this, protocol type is categorical and browser type is categorical. So basically, we need to use an encoder for this. So let's encode this and see this data. Okay. The correlation. Okay, let's see. Attack detected. Failed logins, IP reputation score, and login attempts. Density. Okay. Then we need to load the classifier or the models binary classifier. Then attack detected, accuracy 89, 80, 88, 74, 89. So metrics. Precision. Okay, let's check it. This one. Um, the model used here is the random forest. It has 100 decision trees. Each tree is trained on random subset of data and features. Final prediction is made by majority vote. Then we have gradient boosting. It iteratively builds trees where each new tree corrects the error of the previous. It uses a learning rate zero point 0.1 to prevent overfitting. We have MLP neural network that use ReLU activation. And we have standard scaler and label encoder. So basically, what I can see it is that I think we can only use this three three features, which are the login attempts, IP reputation score, and failed login, because this feature has the most positive correlation within our dependent variable, which is the attack detected. So this Kaggle notebook has no that kind of experimentation, and I think that is the gap of this notebook, because it use all the features available. Let's proceed with the connection to the neural networks. So the NN concept demonstrated in this notebook is the feed forward architecture. We have input layer 1, layer 2. Then ReLU activation, we were using ReLU. Back propagation that computed the entropy, and gradients are propagated backward through layers. Then feature scaling, we sure that we standardize our data or our value. Then output layer and sigmoid and loss function. So this is the architecture diagram. We have input layer, 50 neurons, one per feature. Then hidden layer, 64 neurons. We're using ReLU activation. Hidden layer 2, we use activation ReLU, and the output, which is the sigmoid P intrusion. Then for section 3, we have different variants. Demo 1, we have standard evaluation output, which is this is the classification report. Then demo 2, single sample prediction, input variance. So we're using normal session, suspicious, and borderline. Then this the report. Then demo 3, this is the predicted and predicted 0 and predicted 1. We have 1741 true negative and 1085 true positive. Then this is the demo for the effect of MLP performance. So for this takeaway, we have six. Neural networks solve real security problems. This activity shows that neural networks are not just academic, but they can be deployed in intrusion detection system that protect actual networks. The MLP classifier trained here mirrors what enterprise security tools use to flag suspicious behavior automatically 24/7. Feature engineering is as important as the model. Raw features like IP reputation score, failed logins, and unusual time only becoming meaningful after encoding and normalization. Because as you can see here on our on our correlation matrix, we just saw those three: login attempt, IP reputation score, and failed logins. So I think we can only use these three columns. Then third, architecture choices directly affect performance. Yes, because we need to somehow do experimentation like changing hidden layers, activation function, or training iteration. Um, each of this is a hyperparameter tied directly to the neural network theory covered in our class. Fourth, in security, recall matters than the accuracy because um, when we talk about recall, it needs to capture it is the capability to capture all the unusual attack or the intrusion prediction for this. So basically, we we are always considering what is the right metrics for this. If you are using accuracy, precision, or recall, because recall all the true positive while capturing all the unusual attack for this. Then fifth, MLP versus ensemble methods. We need to know our data. The, we need to compare every model that we know that can help to understand this project. Number six, borderline prediction expose the probabilistic nature of NNN. Then, final reflection. This activity powerfully connects classroom theory to a tangible, high-stake domain, protecting computer network from attacks. Building an intrusion detection classifier using an MLP neural network reinforces the full pipeline from raw data pre-processing to forward propagation, loss minimization, and evaluation metrics. It also teaches intellectual humility. Sometimes a random forest outperforms a neural network, and knowing why is the mark of a truly capable practitioner. We don't need always neural network. We can use traditional uh, machine learning method because not everything can be solved by neural network. And that's all. Thank you.